Any questions? Resume share. Okay, any questions? Okay, so let's look at some other examples. Okay, so for example, this can be generalized to R3, right? So for R3, we can talk about the standard basis, which is 1, 0, 0, 0, 1, 0, and the vector 0, 0, 1. Okay, so this is called the standard basis. So this is special basis, okay, from a standard basis. Sometimes in physics they are called the IJK vectors. Okay, so this idea can be generalized to Rn, the vector space of n vectors. And let's talk about some different examples. I won't do the same thing for this one. Let's talk about basis vector for vector space of polynomials. Okay, so let this V be the P2, which is a set of polynomials of degree less than or equal to 2. And let's consider this set t squared plus 1 and t minus 1. And the third vector is 2t plus 2. So the question is S a basis? A basis, okay? So we have seen that we can write different bases for the same vector space. So this is S a basis for P2. Let's look at the solution. Okay, so the first step is whether these three polynomials are linearly independent. Okay, so we first check linearly independence. Okay, so for that we write A times the first vector plus B times the second vector plus C times the third vector equals 0 vector, which is the 0 polynomial, and we are asking the question whether there's a solution of this equation other than A equals B equals C equals 0. Okay, because if I choose A, B, and C equals 0, then this is always a solution. So we are looking for non-trivial solutions. Okay. Okay, so we did this before, right? So you see t squared term has coefficient A. So A must be 0. Let me write it. Okay. So A times t squared plus, let's look at the coefficient of t, which is B plus 2c. And then the constant terms are A minus B plus 2c. These are the constant terms. And this equals 0. Okay. So from here, you see A should be 0 and B plus 2c should be 0. And finally, A minus B plus 2c should be 0. So what is the solution of this one? So A is 0, and if I add the second and third equations, I get 4C equals 0, right? Which means C must be 0, and if C is 0, then B surely must be 0. So there's only trivial solution. So only trivial solution. If there's only trivial solution, then this set is linearly independent. Okay. So yes, this set is linearly independent. Now let's check. The problem of span. Whether these three vectors span the vector space, the whole vector space. So what does this mean? So this is question. We don't know it yet. So let's look at it. Okay, so what does it mean to be span? So span means if I take any vector here in P2, I should write it as a linear combination of vectors in S. Okay, that's the definition. So let's take any polynomial in P2. What does it mean? So I have to take the coefficients arbitrarily, like A, bt plus c, something like this. Okay, this represents all the polynomials in P2 because A, B, C are undetermined right now. And we want to write it as a linear combination of vectors in S, which means A1 times t squared plus 1 plus A2 times the second vector, which is t minus 1, plus A3 times the third vector, which is 2t plus 2. Okay, so we want to know whether we can solve this system for any ABC. Okay, so we want to find A1, A2, A3 in terms of A, B, and C. So we can represent this as a matrix equation as usual. So what does it give us? So we have already, in fact, wrote down the equations. So this means A1 should be A. So I'm writing the same equation as here. Okay, so the second line now is A2 plus 2A3 equals B. And finally, we have A1 minus A2 plus 2A3 equals C. So the question is whether this system has a solution for any ABC. Okay, so how can we see that? Okay, from here, we already found A1. A1 is solved. Now we get two equations in with two unknowns, right? So this means A2 plus 2A3 equals B. And if I plug in A to A1, then I get minus A2 plus 2A3 equals C minus A. Okay, so we have two equations with two unknowns because the first variable is already solved. Okay, so what does this give us? Can we solve this? Yes, so if I add these two equations, then I get 4A3 equals B plus C minus A, and I can solve for A3, right? So I get the solution for A3, and I can also solve for A2. How can I solve for? If I subtract these two equations, if I subtract them, then I get rid of A3, and I get also 2A2 equals B minus C plus A. Okay, so the short answer, so the summary is we can solve this. So we found A2, from here we found A3, and from here we found A1. So A1, A2, and A3 can be solved in terms of A, B, and C. Okay, A, B, C are arbitrary numbers here that we don't know. Okay, they're arbitrary. And we can solve them. We can make this equation satisfied by choosing A1, A2, A3 like this. Okay. Is this okay? So the answer to this question is yes. Yes, span of S is P2. There was an easier way of doing the second part. What was the easier way? Okay, so the easier way is this. So this problem is finished. So there's an easier way of doing, in fact, both parts. Recall. Suppose A is a n by n matrix, and we are considering the equation AX equals B. Okay. Then we can always solve this equation for X in terms of B if A has an inverse. Okay, so if A has an inverse, or if the inverse of A exists, then we can solve this equation as X equals A inverse B. We have talked about this. So, and we have seen that A inverse exists. When does it exist? So we have found the necessary and sufficient condition for the inverse of a matrix to exist. That condition was, again, this incredible tool, which is determinant. If this determinant is non-zero, then we said that its inverse exists. Okay? So now let's look at this equation. This equation over here is really something like this. Okay, so 1, 0, 0, 0, 2, 2, and then 1, minus 1, and 2, A1, A2, and A3 equals A, B, and C. Okay, so this equation has a solution for any given ABC if and only if the determinant of this matrix is non-zero. Okay, so we didn't really need to know what the solution is. We only wondered whether there's a solution. And the answer depends on the determinant of this matrix. If the determinant is not zero, then the answer is yes. We can solve this for any given ABC. If the determinant is zero, then this equation will not have a solution for some choices of ABC. Okay. So for the second part here, what we could do was we could just check the determinant and see that it is not zero. If the determinant is not zero, then the answer to this part is really yes. And interestingly, if the determinant is not zero, then the answer of the first part is also yes. They are linearly independent. We have seen this, right? We have seen that if we should really check the determinant. Where did we do it? We did it somewhere. We did it somewhere. Where was it? Yeah, I think we did it here. So we looked at this equation. If the determinant is zero, then there are not some non-trivial solutions, and it is linearly dependent. But if the determinant is non-zero, then the only solution is the trivial solution. So for this example, just checking the determinant of this coefficient matrix was enough. Okay, so let's let's write it here. So for the previous problem, it is sufficient to check determinant of the matrix, which is 1, 0, 0, 0, 2, 2, 1, minus 1, and 2 is non-zero. If this is non-zero, then these three vectors form a basis. Any questions here? İkinci row 0, 1, 2 olmayacak mı? Yanlış mı yazdık? 0, 1, 2 çok güzel dedin. Şurası 0, 1, 2 olacak değil mi? Şurası da 0, 1, 2 olacak. Teşekkür ediyorum Barış Yazar. Any questions, guys? So this determinant seems to be really, really useful. So it saves a lot of time. So look at what we have done here. So we did a lot of work here, but we could simply just look at the, so we did a lot of work here. We could just simply look at the determinant of this coefficient matrix. That was it. And same for example, for this problem as well. So we could just look at the determinant of the matrix 1, 0, 1, 1. So if we could see that it is 1, which is not 0, then it will give us that these vectors are linearly dependent, as well as these two vectors span R2. We can represent any vector xy in terms of these two vectors. So you should really just check the determinant of this coefficient matrix. That's it. Okay. Okay, usually the problem will be not to check whether given a set of vectors is a basis, but actually try to find a basis for the given subspace. Okay, that's the real problem. So we want to express a complicated vector space by this basis vectors. Okay, so you see R3 is like a big like vector space. It has infinitely many solutions, but we can represent it with just these three vectors, ijk vectors. We can write any vector we want in a unique way by using these three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so if we are given some specific subspace, what we really want to do is we want to represent it with the basis vectors, so that we can write any vector in that vector space in a unique way using those vectors. That's the main idea. So we will now work on this problem. Okay, now the question is, so let's say V is P2 and W is a subspace of V such that W consists of the polynomials of this form, AT squared plus BT plus C, but let's write this A minus B here. Okay, so this is subspace of V. Okay, so in fact, one should check that this is a subspace. So I'm leaving you to check this is actually a subspace. Okay, so to be a subspace, if you remember, the condition was if you consider any such polynomial, any two polynomials of this form, then their sum is also a polynomial of this form. And if you take a if you take a scalar product with a scalar, then the result is still a polynomial of this form. Okay, so this W is really a subspace. Okay, so if I can give, for example, let's give an example. For example, I don't know, 2t squared plus 3t minus 1 is in this space. Okay, is in W. But let's give another example, which is 3t squared plus 1. This is not in W, right? This is not in W because the constant term must be like in the form a minus b. Okay, so now what is the question? I didn't write the question yet. The question is this. The question is find a basis for this subspace. For W. So we're trying to express this complicated vector space by few vectors, okay? 1, 2, 3, some like few number of vectors in a unique way, okay? So here this is important. Find a basis because we know that there will be different basis vectors. We can choose different basis vectors, okay? In fact, there will be infinitely many different basis vectors. We want to find just one of them, okay? Any one of them is fine. Okay. So how can we do this? How can we do this? So it's not very difficult. We can choose one basis vectors. So let's look at the solution. So 8 times t squared. So the vectors in this W is of this form, bt plus a minus b. And if I take this into a and b parentheses, what do I get? I get t squared plus 1 plus b times what? T minus 1. Okay, so what does this tell us? What does this relation tell us? Did we find the solution? We can take two vectors. Yes, we found the solution, right? So you see, any polynomial in this subspace can be represented by these two polynomials, t squared plus 1 and t minus 1. So as a basis vectors, we choose the basis vectors as S. So these two polynomials, t squared plus 1 and t minus 1. Okay, so now the point is now show S is a basis. Okay, so we should show that it satisfies the conditions of being a basis. For, of course, for which space? For the space W. We should show this. Okay, so how do we show it? So for part A, we have to show linear independence. How do we show linear independence? Well, take any linear combination of it plus b times the second vector equals to 0 vector, and look for solutions of this system. Does this system have non-trivial solutions or not? So you immediately see that the coefficient of t squared is a, so a must be 0. Otherwise, it cannot, the equation will not be satisfied. But if a is 0, then b must surely be 0. Okay, So there's only a trivial solution. We should say only trivial solution. So only trivial solution means what? Only trivial solution means linearly independent. Okay, so this part is done. Now let's look at the second part. So whether span of S is W, what can we say about this? What can we say about this? Okay, so we already did this actually. So we showed that the span of S is W. Why? Because we wrote it here. So any vector in W, which must be of this form, can be written as a combination of t squared plus 1 and t minus 1. We already did this one. So this is true. Okay. So yes, S is a basis. We found the solution. Good. Yes, Nesrin, you're right. So this is a basis, and that's it. Okay, so here there's a something about uh, dimension. Okay, so what is dimension? Okay, let me define what is dimension. So let V be a vector space. Okay, and let S be a basis of V. Now, if the set has infinitely many vectors, so this is the symbol for infinitely many, right? So if the set S has infinitely many vectors, then this vector space V is called infinite dimensional vector space. So we haven't seen examples of this. Oh, we have seen an example of this, but we didn't touch it too much. So we just saw it for a brief moment and then we were done. In this class, we will never work with infinite dimensional spaces, okay? But there are such spaces and they are very important for mathematics and physics, but we won't be doing with anything about that. If S has finitely many vectors, then V is called a finite dimensional vector space, okay? So if S has finitely many vectors, then V is called finite dimensional space. So in this class, we will always be talking about finite dimensional vector spaces. Yes, and final thing. So in this case, number of vectors in S is called the dimension dimension of the vector space. Okay, so let me make this thing. Where's my? So let's highlight this term. So this is called dimension of V, number of vectors in S. Okay, so if S has infinite many vectors, it's infinite dimensional. There will be infinite dimensions. And if S has finitely many vectors, for example, if S has 3 vectors, then V will be a 3-dimensional vector space. Okay, so there are some issues with this definition, guys. So there are some things that I skipped. Let's try to find them. The first issue is this. I said let S be a basis of V, but how do we know that a given vector space has a basis? So the question is this: are there vector spaces which do not have a basis? And the answer is complicated. So the answer is complicated. So yes, the answer is complicated. The mathematics separates into 2 parts. So in one part, there are 2 mathematics. In one mathematics that we're all doing at the moment, every vector space has a basis. There is another mathematics which nobody is doing except for like some crazy people. And in that mathematics, there are vector spaces which do not have a basis. So this is a very fundamental axiom of mathematics. So of course, none of these things are included in this class. Okay, so it's the idea is axiom of choice. So there's a mathematics. So let me just write the name. So axiom of choice. So if you have time, just look it on Wikipedia or YouTube, whatever. Axiom of choice. So this is a fundamental axiom of mathematics that we're all doing. Okay. So this axiom guarantees that any vector space has a basis. Any vector space has a basis. So as I said, but this is an axiom. What does it mean? It means we take it for granted. Okay, so there is no proof for this axiom of choice. So there are no proofs for axioms. Those are the things that you take as granted. So if you don't accept this, there's still mathematics you can do. That mathematics has very bizarre conclusions. Like in that mathematics, you can take a ball, you can somehow cut that ball in some pieces, and you recombine them to get 2 balls. So one ball magically becomes 2 balls in that mathematics. So we won't be doing those kind of things, of course. Okay, so any vector space will for us, any vector space will have a basis. That's the first issue. The second issue is, so here it says a basis. Okay, so because we said that there can be different, we can choose different basis vectors for the same vector space. So what happens if we choose 2 different basis vectors and they have different number of vectors in it? Can something like this, is something like this possible? The answer is no. So the answer is independent of which basis vectors you choose. Okay, so if there is one basis, if one basis has m vectors, and if you choose another set of basis vectors, those the number of those vectors should also be n. Okay, So the definition is independent of the chosen basis, okay? So this is a theorem. This can be proven, which we won't do. The number of vectors in S is independent of S. Let's call it, let's say it's like this. So if you choose different basis vectors, it will have still same number of vectors. So what do I mean by the second thing? So what I mean is this. So let's go back. Let's go back to first example. So we discussed that this is a basis set of basis vectors. Okay, it has two vectors. So the dimension of this space is 2. And later we gave another base set of basis vectors, and it still has two vectors in it. So it couldn't have 3 vectors, or it couldn't have 1 vector, or 4 vectors. It must have 2 vectors. So the number of vectors is independent of which basis you choose. It will always be 2 for this vector space. Okay. So again, for this vector space, all the basis vectors will consist of 3 vectors. The number will not change. Okay, guys. These are all very interesting. And this axiom of choice is something very interesting. Let me look it up on Wikipedia. So Wikipedia, axiom of choice. So this axiom of choice really says that if I have like infinite collection of sets, then I can choose one element from each of those sets to combine it to make a new set. Something very trivial like this, which cannot be proven by the other axioms of mathematics. Okay, this is independent of the other axioms. So it was formulated in the early 20th century. So anyway, let's not go too much into it. Okay. Any questions from here? Okay, so let's do some examples, and then yeah, our time will be up. Okay, so let's do this example. So let's take some vectors v1, 1, 0, 1. Maybe I should write them in column format. That will be easier to write. And v2 will be 0, 1, 1. And v3 will be 1, 1, 2. And v4 will be 1, 2, 1. And v5 will be -1, 1, -2. So these are 5 vectors. Now what is the question? Let's call this 5 vectors the set V. Now the question is this: find a basis for the set Span of S. Oh, not a question mark. Find the basis for the span of S. We should omit some vectors. Yes, we will omit some of the vectors. Okay, so there are 5 vectors, but these are like 3 vectors, which means they have 3 components. So we know that the dimension will be at most 3 and possibly lower. Okay, it could be span of S could be like 2-dimensional or 1-dimensional. From the looks of it, it looks like there will be at least 2 dimensions. So it can be 2-dimensional or 3-dimensional. We don't know right now. Okay, span of S. Okay, so first thing, span of S, we talked about this. This is the set of all possible linear combinations. And this is always a vector space, okay? So we're only talking about dimensions or basis of vector spaces. And span of S, no matter what S is always a vector space, okay? Of course, we're talking about S non-empty. If S is not empty set, then it doesn't make sense. Okay, so, oh, the question was not, was the question this? Let's, the question was not this. Find the basis for span of S. Okay, let's answer this question. Solution. Now, now our aim is to find redundant vectors in this 5 vectors. Okay, so what we do is we write a linear combination of these vectors a1 v1 plus a2 v2. I don't want to write all of them, plus a5 v5 equals the 0 vectors. Okay, this will give us an equation. What kind of equation? So a1, so this will give us basically this equation, matrix equation. And the 4th vector and the 5th vector. Okay, so this times a1, a2, a5 equals 0, 0, 0. So I'm really solving this augmented equation. Then what I do is try to bring this into row echelon form or reduced row echelon form. Now I won't do this. We have studied this before. Let's just write the final answer. Then what do we get? We get something like this: 1, 0, 0, and 0, 1, 0, 1, 1, 0, 0, 0, 1, and -2, -1, and 1. This is 0. Okay, let's write the zeros here as well. Okay, let's look at this row echelon form. So which are the leading ones? So leading ones are the first non-zero or first ones in each row. So here I have a leading one. Here I have a leading one. Here I have a leading one. And remember that this column is a1 column, a2 column, a3 column, a4, and a5 column. So a1, a2, a4 has a leading one, and a3 and a5 does not have a leading one. Okay. So what does this tell us? This tells us this system has infinitely many solutions, first of all, infinitely many solutions. And a3 and a5 can be chosen as free. Then I will have then I can solve a1, a2, and a4 in terms of a3 and a5. Okay, maybe I should write the solution, doesn't matter, but So we can write the solution. For example, what I said, A3 is arbitrary. Let's call it R. A5 is arbitrary. Let's call it S. Then I can solve, for example, A4 in terms of A5, which is minus S. And A1 is really what? A1 is minus R plus 2S. A2 is what? A2 is minus R plus S, right? I'm basically solving these equations. If I do that, I get this equation. So there are infinitely many solutions with 2 parameters. This shows us what? This shows us basically I can choose span of S as the vectors which have a leading one, and those vectors are vector 1, vector 2, and vector 4. Why? Because I can express vector 3 and vector 5 in terms of the other vectors. Okay, so yeah, that's it. So these 3 vectors are sufficient to span this space. The other vectors are redundant. Okay, so this is really a basis of the span of S. No, we cannot say the opposite. We cannot say the opposite. So suppose we remove V3 and V5. Then what we get in the reduced row echelon form of the remaining vectors will be like this. Okay, 1, 0, 0, 0, 1, 0, and the fourth column is 0, 0, 1. Okay, so we would get something like this. So you see this matrix has determinant 1. So these are really the linear independent vectors in this set. Okay. Okay, we don't have time today. Neye göre seçtik? Yani şuna göre seçtik aslında. Burada leading one'ı olan vektörleri seçtik. Tamam. Burada 1, 2 ve 4'ün leading one'ı var. Onları seçtik. Yaptığımız şey bu. Bunun hakkında yarın biraz daha konuşacak. Bugünlük burada bırakalım arkadaşlar. Bu materyali siz bir daha tekrar edin. Okay. Yarın bu kaldığımız yerden bu sorularınızda başlarız. Okay. Evet arkadaşlar, katıldığınız için hepinize teşekkür ediyorum. RRF formunda mı olmak zorunda sadece? RF olsa da görebilirdik, evet. Yarın buradan devam edeceğiz arkadaşlar. Herkese iyi günler arkadaşlar. Görüşmek üzere yarın. Kendinize iyi bakın.